Alright, how you doing? Today my name is Primeaux. I'm going to be the lead for the air conditioner experiment that my group's going to be doing next week, and that is group 4. Here's just an outline of what I'm going to be talking about. Let's start with an introduction. I'm going to talk about the theoretical background behind air conditioners and heat pumps in general. Then I'm going to go over the goals for the experiment, talk about the apparatus, explain the procedure of how to do the experiment, and then talk about the COP, and I'll explain what that is later. So first off, like I said, an air conditioner is at base, it's just a heat pump, and all that means is a device that's used to move heat from a source to a sink, the source being a lower temperature environment to a higher temperature environment, which, as we know, is not what heat normally wants to do, so it needs work to work against the temperature gradient. So here you see a temperature entropy diagram of the cycle, the refrigeration cycle that air conditioning units use. You start right here on the curve at a saturated vapor at 0.1. It's going to go through the compressor up to 0.2. It's going to be a superheated vapor. From there, it's going to go to the condenser. It's going to go from 2 to 3, which is just along that isobar, to back to the curve, then through the curve, where it's then going to be a saturated liquid. Then it's going to go down to step 5, where it's going to be liquid vapor, and then back to step 1 across the evaporator. And this right here is just a pH diagram, pressure entropy diagram of the same process. You can just see what it looks like there, same steps. Goals for the experiment are just going to be to learn how to perform the thermodynamic analysis of an air conditioner. We're going to talk about how different charge levels, which is really just different freon levels, affects the performance of the air conditioning unit. And then we're going to find the COP of our air conditioner. Here's the apparatus. It's like I said, you can just see the components that I've been talking about in this cycle. It's not too much different. The main thing is we're going to have a couple different locations where we're going to measure pressure and temperature so that we can calculate our enthalpies, which is what we're going to eventually use to calculate our COP. So procedure. First, we're going to start and make sure that at rest, not on, that all the measurements of temperature and pressure are the same. Of course, they should be the same if it's all sitting here in an ambient environment. If they aren't, we're going to have to calibrate them to make sure they're the same. From there, we're going to go ahead and add freon from the storage tank until it reads about 14 pounds, and that's the charge that we're talking about. And then we're going to allow the system to reach steady state. At this point, we're going to measure the exit and entrance temperatures around the evaporator, and then we're going to use then we're going to find the velocity of the air in the evaporator. And then we're going to do a couple different levels of charge and calculate these same measurements and then shut it down. Alright, so I've been talking about COP. That's kind of the main value that we're going to want to try to calculate and take away from this experiment. So what it basically is a ratio of the desired commodity. In our case, that's the heat. It's a ratio of the desired commodity to the power consumed, which we're going to be concerned with the power consumed in our compressor. And we're going to estimate using values of enthalpy calculated from pressure and temperature at those locations like you saw on the last slide. For our case, it's going to be 1, 5, 2, and 1 of the places where we're going to find enthalpy. So for my initial calculations and predictions, the first enthalpy is the enthalpy at the saturated vapor point. I found that to be at 500 kilopascals. I found that to be 405 kilojoules per kilogram. Then I had to find a way to find the enthalpy of the superheated steam. So I chose a temperature of 35 degrees Celsius, and online it said that most compressors operate at a temperature about 15 degrees above the ambient, which for our case would be about 35 degrees. And they told us that this thing runs at about 1200 kilopascals. So then you get this 418 kilojoules per kilogram enthalpy. And then the last enthalpy is the enthalpy of the liquid vapor, which you need to know the quality of the vapor to really find. I think I chose a quality of about 0.5. I came up with about 302 kilojoules per kilogram. And putting all those things in the equation, you get a coefficient of performance of 7.92. And it is an ideal calculation, so it is a little high. And in our experiment, we're probably find lower values than that. Does anybody have any questions?